Hello everyone. Let me start with a simple question. Have you ever noticed how a coin at the bottom of a glass of water looks a little higher than it actually is? Or how a straw dipped in a glass of lemonade looks bent at the surface? These are not magic tricks, they're physics in action. Whenever light passes from one medium to another, say from glass or water into air, it bends. This bending is called refraction. At the same time, a tiny portion of the light also reflects back into the denser medium. Now, here's something important. When light moves from a denser medium like glass to a rarer medium like air, the refracted ray bends away from the normal. That means the angle of refraction, R, is always greater than the angle of incidence, I. Now let's explore the first case. What happens when the angle of incidence is small? If the incident angle I is less than a special value called the critical angle C, most of the light passes into the rarer medium. Only a faint, weak reflection remains inside the glass. For example, when a ray now hits the glass air boundary at a small angle, it gives a very weak reflected ray OC and a much stronger refracted ray OB that bends away from the normal. This is the very reason why when you look at objects underwater, they don't appear at their real position. Your eyes receive the refracted rays, and that makes the object look slightly displaced. Now comes the turning point, the critical angle. The critical angle is defined as that particular angle of incidence in the denser medium for which the refracted ray in the rarer medium just grazes the surface. In other words, the angle of refraction becomes exactly 90 degrees. Mathematically, Snell's law gives us the relation sin of C equals refractive index of rarer medium divided by refractive index of denser medium. For glass with refractive index 1.5 and air with refractive index approximately 1, the critical angle works out to about 42 degrees. Look at the diagram. When the incident ray hits exactly at C, the refracted ray does not emerge into the air but runs along the surface, making an angle of 90 degrees with the normal. Now, what if the angle of incidence is even larger than the critical angle? In this situation, no light escapes into the rarer medium. Instead, the entire ray reflects back inside the denser medium, just like a perfect mirror. This phenomenon is called total internal reflection or TIR. Notice that in this case, the laws of reflection still hold true. The angle of incidence equals the angle of reflection. But all of this takes place within the denser medium itself. This is not just a classroom concept. TIR is the working principle behind fiber optic cables, the sparkle of diamonds, and even the shimmering mirages you see in a desert or on hot roads. Let us now derive the relation for the critical angle step by step. According to Snell's law, refractive index of denser medium, N1, times sin of I equals refractive index of rarer medium, N2, times sin of R. At the critical angle, I equals C and R equals 90 degrees. So, N1 sin C equals N2 multiplied by sin 90, which is just 1. Therefore, sin C equals N2 divided by N1. For example, if light is passing from water with refractive index 1.33 into air, sin C equals 1 divided by 1.33. Calculating this gives us a critical angle of about 48.8 degrees. This formula is the key to predicting whether light will refract or totally reflect. Let's solve a quick example together. Suppose a ray of light passes from glass whose refractive index is 1.5 into air. First, we calculate the critical angle. Step 1. Use the formula sin C equals N2 over N1. That is 1 divided by 1.5. Step 2. Sin C equals 0.667. Step 3. Take the inverse sine of 0.667, which gives us about 41.8 degrees. Now let's check. If the angle of incidence is 50 degrees, is total internal reflection possible? Since 50 is greater than 41.8, the answer is yes. The ray will undergo total internal reflection. This step-by-step approach shows how the formula directly connects theory with actual behavior of light. So let's wrap up. When light goes from a denser medium to a rarer medium, three possibilities arise. If the angle of incidence is smaller than the critical angle, the light mainly refracts and bends away from the normal. If the angle equals the critical angle, the refracted ray just grazes along the interface. And if the angle of incidence is larger than the critical angle, no light comes out. Instead, total internal reflection takes place. Remember, the condition for critical angle is given by sin C equals refractive index of rarer medium divided by refractive index of denser medium. These principles are not abstract, they power technologies around us, from the brilliance of diamonds to the internet running through optical fibers to the mirages that trick our eyes in deserts. I hope you now have a clearer understanding of how light behaves when it tries to escape from a denser medium. See you in the next session with another fascinating journey through the world of physics.